Okay, great. Good morning, everyone. I am a physicist by training, and I've become a geophysicist, so my geology is not as good as yours, so you'll forgive me for that. In this talk, I'm going to look at the geophysics that we've done for the state, as well as some other techniques that might be useful for you. So my goal is really just to inform you about what the different methods can do and how you might be able to use them. So CEG has acquired over 150,000 line kilometers for the state of Alaska over the past 20 years or so. The geophysics has included frequency domain EM with the DIGHEM and RESOLVE systems. There's a slight difference, and I'll get to that later, as well as magnetics and radiometrics. We also have a number of surveys for private companies in the state. We've flown 70,000 line kilometers there, so we have a lot of experience working in Alaska. It has been predominantly helicopter-borne geophysics from that we've done. So this is, can you see this? So flying the EM is giving us information about the rock conductivity, the magnetics for magnetic susceptibility, and the radiometric or gamma ray spectroscopy is for natural radio element concentrations. And by combining these different rock properties, you can start to get a better picture of the what's going on in the subsurface. So it's really looking at all the different available geophysics. Airborne is really useful for access and for speed of coverage. We're able to cover way more ground than you could with anything else for a lower cost. So it's a really effective tool for these large-scale surveys. So first I'm going to talk about the electromagnetic technique. Just a summary of what the takeaways should be. EM is detecting electrically conductive material. Sometimes this is direct detection of deposit. Sometimes this is mapping alteration zones. Sometimes this is mapping conductive overburdens. So there's some interpretation involved. The resistivity or conductivity, I use the terms interchangeably, they're the opposite of each other. Resistivity is controlled by mineralogy as well as by the porosity, so how much water is in some, how much water can be in a rock, the saturation, how much water is in there, and the salinity, how conductive or how saline that water is. In order to properly use the geophysics, you need to understand the properties of the target as well as the properties of the host. We need to be able to detect some sort of physical property contrast. So if they're too similar, geophysics isn't going to tell you too much. And there's a lot of different EM systems that you can choose from. So how does the EM technique work? We have our transmitter coil with the TX and our receiver coil here. The transmitter sends a pulse into the ground, which causes currents to flow, and those currents cause a magnetic field, which can be sensed by the receiver. When there's something conductive in the ground, the currents concentrate in there, and they decay more slowly. So there's a different magnetic field. So this is how we can detect conductive materials. If we have a conductive layer, it's a similar sort of thing. Currents concentrate in that layer, and we can see the response from them. If there is a resistive layer, currents tend to avoid that. They pass through it very, very quickly. So we can see a sort of a lack of signal when there's resistors present. So all this electrical property stuff is great, but how does this translate into mapping geology? We have our resistivity on top and conductivity on the bottom for a range of materials. We can see our sulfide minerals are very, very conductive. You can also see that there's a very wide range, there's a 2 order of magnitude difference in resistivity, and it overlaps graphite. So there's cases where we can tell there's something conductive there, but we might not be able to tell whether it's sulfides or whether it's graphite. And in this case, whether it's seawater. So there's sometimes you can make the distinction, but there's interpretation involved. What else is interesting? We have some of our clays here. They're fairly conductive. Tills and gravels and sands are moderately conductive, and our igneous crystalline rocks are very, very resistive. We've also done a lot of permafrost mapping in the state. That is very resistive as well. And again, this range here depends on the water content and a lot of times on clay content. So how much alteration there is, because clay is quite conductive. If we look at some of the deposits on the bottom here, we can see that our sulfides are in the conductive end. Vein deposits and formations are going to be resistive. And we just added in the kimberlite, which is moderately conductive. I just wanted to make the point that clay alteration increases conductivity, whereas silica content increases resistivity. So some of the controls on resistivity, it depends on the conductivity of the minerals. So think of that as being sort of the host matrix, as well as the connections needed to have an electrical pathway for currents to flow. So you might have something that's very, very conductive, but if it's sitting in a resistive host, not connected to other minerals, it's not going to look like it's a conductive thing because there's no pathway for the currents. We also are looking for larger zones. They're going to appear to be more conductive. So this is where the footprint of the system is. We're flying 30 meters above the ground. If you're looking for something very, very small, it might be difficult. A fixed wing system will be flying even higher. So its footprint is larger, so the response will become smaller. And I'm going to look at this a bit later on. Water content increases conductivity. Alteration can increase conductivity as well, or increase resistivity. So just some of the controls on what affects the resistivity in the ground. Now, a question that we often get is, how deep can it see? And we always have to say, well, it depends. What are you looking for? How big is it? What is the contrast with the host? And how much cover is there? How much conductive cover can mask EM signals? So with the frequency domain, we usually say at least 60 meters, probably 100, up to 150. Time domain is going to be between 30 meters and 500 meters. So there's a big range there. And just a reminder on the conductivity, we have our graphites and clays being conductive, our unaltered rocks being very resistive, and generally our sediments are moderately conductive. So just a convenient way of dividing up the resistivity on a map that you might see. So what do our targets actually look like? Sulfides are going to be very conductive, except for sphalerite, which is usually quite resistant. Massive mineralization is going to be a nice conductive target for us. Veins are okay, but disseminated sulfides usually appear as moderately resistive. So sometimes we can see those as well. Frequency domain more easily than time domain. And kimberlites and alteration zones are also nice targets for us. The problem we have is that there are other things that are not of interest that produce a response. So we call these geologic noise. We're usually not interested in seeing graphites or clays, but these have a conductive response. Lakes and swamps can also be conductive, but at least we see these as being near surface. It's usually possible to perform an interpretation and not worry too much about those. But when we're talking to the geophysicist, these are the things that we need to know in order to determine if we can see the target that you're interested in. And one thing to point out, the EM response is controlled by the total sulfides, not just the economic sulfides. So often if there's a semi-massive halo around a target, that can be what controls the EM response, and it may or may not be of interest to you. These are some of the airborne EM systems. We have frequency domain on the top, on the fixed wing and the helicopter side. So these are seeing more shallow, but with better resistivity detection. Then we also have fixed wing time domain and fixed wing helicopter domain. There are a large number of systems. We have a lot of choices on the helicopter time domain side. For frequency domain, there's only one fixed wing frequency domain and only a couple helicopter frequency domain. And again, there's only a few fixed wing time domain systems. So you can look around to see sort of what suits you and availability. So I spoke before about the size of the target. This graphic is meant to show how big of an area each system sees at one particular measurement point. The helicopter systems are flying very, very low, so they have better spatial resolution. They're not seeing too wide in this extent. The frequency domain methods have a less depth of penetration. So we're seeing the top 100 meters or so. Time domain systems are more powerful. So time domain helicopter has good spatial resolution and sees much deeper. The fixed wing systems have a wider footprint, so they're more useful for larger targets. The advantage is you can have wider line spacing and still possibly see your target of interest. And this is just looking at the coverage that you can get. Obviously, the fixed wing systems are flying much faster, so you're able to get more coverage in less amount of time. Here we have our transmitter sitting up here, and our receiver is being towed behind and below the system. Our excitation pulse comes down, and we can measure the response from the target. The frequency domain works in much the same way, on a smaller scale. and the receiver and transmitter are both closer to the ground, so you have that better resolution. We're also measuring other parameters during the survey. We have a video camera, so this is really useful for seeing if you've flown over a small lake or some sort of culture or something else that might be giving you a false response. On the EM bird, we have our transmitters and receivers, a GPS sensor, magnetometer, and laser altimeter for producing a digital elevation model and for helping us perform inversions, converting the data to a resistivity. Probably don't want to see too much more of the physics, but I'll go through it quickly-ish. The frequency domain method is always on, so you're constantly generating excitation into the ground and constantly measuring the response from the ground. We separate these into an in-phase and an out-of-phase or quadrature component. And those tell us different things about the conductivity distribution in the ground. Basically, when the transmitter peaks, the amount of signal in the Earth response is the in phase. When the transmitter is 0, the amount of response is the quadrature or out of phase. We are flying with multiple transmitter frequencies. So we have 5 transmitters that are always on. They are operated at different frequencies, and each frequency produces currents at a different depth. So by combining different frequencies together, we can get information about the depth distribution of the resistivity. Now this is the DIGHEM system. We have 5 transmitter coil sets. 3 of them are coplanar, horizontal coplanar, so the loop is sitting like this. 2 of them are vertical coaxial, so it's tilted 90 degrees. The coplanar coil sets are useful for seeing layered structures, or more useful. They both do each thing, but there's a higher sensitivity. Whereas the vertical coils are better for seeing vertical structures. The frequency range is about 900 hertz to 56 kilohertz. We can compare that with RESOLVE, which is our other frequency domain system. It has 5 horizontal transmitter receiver pairs and 1 coaxial pair. So we usually use this more for engineering type problems where you're interested in detecting layers. And it also has a higher operation frequency, so it's better for shallow. Whereas the DIGHEM is more useful for detecting vertical structures. And this chart here is how we usually interpret anomalies when we see them. The panel here shows the vertical coil anomaly shape. So you might be looking for a thin vertical dike, and you get a peak over top of that. With the coplanar coil set, you see this double peak. So right above the target, there's actually no response. So if you are in an area where there's multiple targets, it can be difficult to interpret that, and we'll get to that in a second. But that's the main takeaway. If you have a vertical target, single peak, double peak for the coplanar. And then based on the width of the anomaly, we can get information about the size of that body in the ground. So that's how interpretation is typically done. And this is just showing an example of those shapes when you have complicated targets in the ground. The red is the coplanar, the blue is the vertical coaxial. So you can see immediately where this vertical thing is on the coax. And even for the dipping bodies, you get a bit better spatial resolution. And this peak here occurs right on top of the most shallow part, whereas for the coplanar it's sort of shifted a little bit. So these are all things you need to think about when we're interpreting data. Now, the ratio of these two peaks tells us about the dip. So it's another useful way. We'll see the same body of different frequencies with different coil sets, and this lets us figure something out about the geometry of the body. When we have closely spaced targets, the coax coil set is often easier to interpret. So just something to think about when you're choosing a system. And just another example with some conductive overburden, the coplanars couple well to these layered bodies, whereas the coax don't couple as well. So it sees a better response with that vertical shape. And just a word on the conductance. So conductance is the conductivity thickness of that body. So the more conductive or the thicker it is, the conductance goes up. If the body is relatively resistive, we see a high quadrature signal. If the body is very conductive, has a high conductance, we see a higher in-phase signal. So by looking at the in-phase quadrature components, we can tell about the conductance of the body. This graphic looks at the most sensitive depth of exploration. So how deep is each frequency seeing? On the top here we have resistivity. So if we're in a resistive material, we're seeing quite deep. If we're in, say, a clay around 10 ohmmeters, the highest frequency sees quite shallow, only a few meters, whereas the lowest frequency sees deepest. And in this case, this is most sensitive, so we can see deeper, but this gives a good rule of thumb in the depth of exploration. And we'll see later on that the time domain is seeing deeper still. And this is just an example of a conductivity depth section. So we use the data, we calculate the resistivity for each frequency, and then make this map. So this is, on the top is sort of distance, and this is depth. These lines here are showing the depth of exploration. When we get something conductive, we're exploring more shallowly than when we have something resistive. So depth depends on the resistivity of the host. And if we look at the geology and how deep, sort of what resistivities the different techniques can see, this is our frequency domain in red. So we can see structures that are quite resistive down to very, very conductive. The time domain range is more limited. You get no resistivity resolution for these more resistive things, these gravels with no water in them, and the igneous rocks. You don't get any resolution, but you get more depth. So you have a trade-off there. I just wanted to say a little bit about the DIGHEM data that has been collected by DGGS. Before 1998, this was our system. The MAG sensor was a little bit higher, so that affects the spatial resolution a little bit. In the late 90s, we moved the MAG down to be on the receiver bird. And now we've added laser, which helps us penetrate a little bit of foliage and get a better height above ground estimate. The other major change is calibration. So we used to calibrate the system on the ground, and whatever response we would measure, we'd say, okay, this is 0. And then we'd go and fly the survey. So we had this bias value. So in some areas, it doesn't matter, but if you calibrate it over a conductive ground, the resistivity that you get out at the end will be not 100% right. Everything relative works, so I can still say this spot is more conductive than this other spot, but I can't say, okay, this is clay and this is sand, for example. So around 1999, we switched to a high altitude calibration. So we fly the system up. This is now our true 0, and then we fly the survey. So I know Mark has data from '96. Those resistivity values will not be absolutely correct, but they will be relatively correct. So this spot is more conductive than this other spot. So our precision is the same, but our accuracy post '99 is better. And one other point, for the legacy data, the data was normalized differently. Basically, corresponding to Y2K, we all started multiplying by 2, which brought us in line with what some other people were doing. So if you're using software now for data before 1999, you need to make this switch for everything to work out properly. So just a word of warning. Time domain. How am I doing for time, Ken?
It's quite after. So we'll finish up in 10 minutes.
10 minutes, okay. We can do that. So in frequency domain, we're constantly exciting the ground. In time domain, we hit the ground with an impulse and then measure what comes out of it. This is a high power pulse of energy, and the Earth continues to respond from this after we've turned off that excitation. We then bin this data into little time gates, and we can tell the difference based on the measurements of a poor conductor or a conductive target, based on how long that signal lasts for. Good conductors have a weak early response, but decay slowly, and you can see them at the later time channels. So it's working in much the same way as frequency domain did. We hit the ground with energy, and that current diffuses to depth. And by measuring at different times, we get information about the depth extent. Here is that effective depth of exploration chart I showed before, with the time domain now underneath. So this purple line is sort of our early time channel that's seeing the most shallow information. So for a 10 ohm, or for a few hundred ohm meters, we're looking already 100 meters down. So it sort of continues like this. You can see that the 2 highest frequencies are seeing more shallowly than that first time channel. But these other times are seeing much, much more deeply than the frequency domain is capable of. Whether you can actually see something depends on its contrast with the ground and its size. So this is the points that I had at the beginning. We're responding to how conductive things are, as well as to the alteration. Time domain is power and depth. Frequency domain is for resistivity resolution and spatial resolution. And we'll move on to radiometrics, which we've also collected. We are detecting natural radio decays of potassium, uranium, thorium. We are seeing only information from the top few centimeters. There's no depth information here. This is a great mapping tool because we're directly measuring what's in the rocks. And this is often an add-on for many exploration projects. So what's actually happening? Minerals in rocks are naturally decaying, and they send out these gamma rays. The gamma rays from things that are deep get absorbed by the material above them. So only the very shallow gamma rays go up into the air, and these are what we're measuring. The relationship between rock type and the radio element concentration is complicated, but by combining the different amounts of thorium, uranium, and potassium, you can get this sort of fingerprint for what's in the rock. And for a particular area, there might be a certain ratio. So you can use this for mapping in order to determine the near-surface geology. This is what the equipment actually looks like. We have some crystals in these, which we can tow on the helicopter skid or inside the aircraft. This is flown with fixed wing and with helicopter systems. The higher up you are, the larger footprint you have. So you are looking for larger structures. You're not able to see smaller structures. Whereas with the helicopter on this side, your footprint is smaller. You can detect smaller structures. So we're mapping all types of rocks. We're not able to see through rock or soil or water. So it's very, very near surface. So we have direct detection of uranium. Potassium alteration can often be used for gold exploration. And what we provide is a map of the total counts, as well as the estimated potassium percentage and the relative amounts of the different radio elements. And this is just an example of this map. The total counts are dominated by potassium. So potassium is usually measured in percentage, whereas uranium and thorium are measured in parts per million. So these are relatively weaker signals. And the way, so this is just showing an example of an area where we have our basement rock as well as some transported overburden. So these have different radio element signatures. Over top of the transported overburden, we're seeing very small response. Over top of the water, we're getting no signal. Now, you look at these and it's hard to tell that there's some uranite zone through here. But what you want to do is calculate the ratio of the uranium to potassium, which sort of normalizes for the natural amounts that are coming through here. We can see that we get a spike in the uranium count compared to the potassium. So looking at those ratios is often effective for doing interpretation. And we often see these gamma ray Ternary maps where you are mapping or creating a color based on relative amounts of the different elements. So you're able to correlate this with your known surface geology to get more detail from that. And I'll just say a few words about AGG.
You're good on time. You can go for a while longer, so
Okay.
don't leave anything
I think I want a few slides. So AGG. Here we're measuring the gravity of the ground. It's very, very difficult to do this well because the gravity or the density contrast in the ground is small, and we're doing this from an airplane, which is moving up and down and forwards and backwards. So all those accelerations is something that we are detecting. So we need to be able to remove that noise. There's two techniques. There's actually measuring the gravity and measuring the gravity gradient. And the gravity gradient is more easily able to remove the aircraft ones, but they have different resolution scales. Gravity is more useful for regional scale mapping. We're looking on the order of tens of kilometers, whereas radiometry has a higher resolution. We fly gravity on helicopter and fixed wing. Flying lower and slower, you're able to better resolve features. By combining AGG and VMS, you're able to perform better interpretation, particularly for VMS. So it's really an interesting possibility. We all know about gravity. When we have something dense, it has a greater gravitational attraction. And it's also pointing out here that gravity does not just work vertically, it works in all directions. There's something dense here, there's a gravitational force in all directions from that. Again, we need to measure a contrast. So this red line is just showing what a typical granite might be, and we see a range of different rock types here, or different minerals. Our sulfides are usually quite resistive, and some of the sediments are a little bit less resistive, but there's not much of a contrast. The VMS provides a very high contrast for us, so it's something that's easier to see.
You meant to say density, I know that. You said resistivity.
Usually do EM, so I'm sorry for the density.
It's time zones.
So density is something that's easy to measure. So this is sort of our blueprint for how we do the interpretation. So this is just a reference with this amount of gold at this concentration. There's a 0.07% increase in density. So this is something that's very difficult to be able to measure. You're going to be looking for alteration instead, or looking for a different technique. And this is just showing the density for some different rock types. Generally, more mafic rocks are more dense. There's about a 20% contrast there. So much smaller than the EM, but our sensors are much more precise, so that's not necessarily a problem. And what I wanted to take away here, this is the size of the body, basically. So we're looking on the scale of, here's 3 kilometers, 300 meters. The different lines here are showing the type of technology. So this is satellite gravity. This is telling us that we need something on the order of this size to be seen by that sensor. So you're looking for things in the mantle if you're using satellite. With the fixed wing, things are on the order of tens of kilometers. On the helicopter side, we're able to see smaller structures. So just something to think about when you're choosing helicopter or fixed wing gravimetry. And here is an example of some ground gravimetry versus fixed wing and helicopter. You get much higher resolution with the ground and the helicopter, but in the ground you might be sacrificing access to particular locations, and it's going to be more costly. And that's just my distance scale there, 20 kilometers. So low and slow gives you that resolution. And one thing that we have to account for is the terrain. So if you have a nice flat situation, everything's easy, we perform our measurements, and we're done. When we get into areas with topography, our gravity situation becomes much more difficult. Now we're actually getting this mass here pulling our signal up. So we have a decrease in signal, not because of what's happening underneath us, but because of the mountains on either side. Similarly, if we're flying over the peak, we were expecting to see mass and rock there, but we're not. So this is something that we spend a lot of time correcting, and we are acquiring a digital evolution model with a laser scanner. And this is just an example from a kimberlite. This is the data as recorded. And the map is dominated by the void left from drilling. By calculating our DEM, we're able to correct that, and this is the map we get out, and a number of our known kimberlites start to show up that you can't see here. So terrain can add a complication to us, which we're usually able to correct. And just an example of spatial resolution and the effect of flying lower. Each of these curves shows the response from a different altitude. So flying low to the ground, we're closer to that gravity source, it has a higher impact on our signal, and we get a much higher anomaly from that. If we look at the Caddy mine, we have our fixed wing response up here and our helicopter response here. I think this is the Caddy, but these are known kimberlite targets, and they're much more evident in the helicopter grid than in the fixed wing grid. That's the Caddy response. So here's the actual response measured by the systems. This is height above ground for fixed wing in blue, and this is the measured gravity gradient. There's a big anomaly in the helicopter and only a very subtle anomaly in the fixed wing. So just a few key points. We are measuring density contrast, and our instruments are very sensitive with the gravimetry and radiometry. Radiometry has more resolution than airborne gravity, and the helicopter has better resolution still. We're constantly improving these systems, and we have something new coming out in a few years. So we're starting to reach the sensitivity of deposits that are actually too small to be economic. So our resolution is getting quite good. By combining gravity with EM, it provides a very powerful tool for finding EMS. And if you're looking at just gravity, you're looking for very big targets. And that's all I have. Thank you very much.
Any questions for Nate?
Got 3, bear with me. 2 on the EM. The first one, if you are in an area, say, with extensive permafrost, so you have a very low resistivity zone near surface, are you going to, you're not going to get much response in that zone, but is it going to attenuate any of the signal below it, or will you still get relatively good data below those low resistivity zones? Like the seismic, right? It's hard to see anything below permafrost, but
so the permafrost is actually really resistive.
Right. Sorry.
Right.
Awesome.
So we absolutely see things very well beneath that permafrost. Depends. So how thick is the permafrost? Tens of meters.
Sure.
Yeah. So depending on what the target is, seeing through that permafrost is no problem, and that's something that we have been looking at using the EM for seismic data correction.
Right.
So mapping that permafrost zone, so that's pretty easy for us. We have that resistor and a conductor. We can map the thickness of that zone and use that as an input to the seismic data processing.
Right. My other question.
I'll add permafrost and talk twice more on that area.
Oh,
So
okay.
I can tell you a little bit.
Great. When you were talking about processing for the prior to 1990, the ground calibration
Yes.
versus the high altitude calibration, is there a mathematical correction you can do to the data prior to 1999, or is that, has that been looked at, or is it not worth it? It's relatively minor if you're trying to compare data sets.
Have you looked at this before, Ken? No.
We've looked at the factor of 2, and we built that in because that was well defined. The calibration thing is a little, how long is a piece of string on a particular day?
Right.
I guess the old caveat emptor, just, if you've got something you're flying over and you do some sort of empirical calibration, get yourself comfortable that the data is seeing what you want to see, even if the units are, we tend not to be slavish to saying it has to be a certain resistivity or a certain conductivity. It's like if it's low and it's high, the relativism is usually what we work with from a point of view of saying what's an anomaly. And on the units, Adam mentioned the resistivity and conductivity are the reciprocal of one another, but geophysicists don't let geologists get away that easy because historically, resistivity is assigned to DC resistivity surveys as done with IP. And it's also about the range of units. Sitting about 1 Siemens and 1 ohm meter, below that, where it's more conductive, people tend to say it's a conductivity zone, and we put them into units that flip, and it's easier to say, I've got 100 Siemens or 100 millisiemens, whereas going resistive, it's easier to say it's 10 ohm meters or 100 ohm meters. But then you have to, and where it is if somebody makes a plot and they put resistivity on the map and they don't tell you what the system is, that might be an inductive system or it might be a DC resistivity system. And the two are not the same over the same feature. That has been demonstrated that when you put a current in the ground with an inductive system versus torturing it with electrodes and current with like an IP system, those values are often different because the flow patterns are different. And Adam touched on that. One kind of flows through the whole rock, and the other goes through interstitial spaces, grains where there's fluid, and then it hits a sulfide particle. So it's something to keep in mind if you see that they are, at a simple level, they're reciprocal of one another, but you have to know what the acquisition system was to understand the two. And again, it's sort of like, don't sweat it. If something is in DC resistivity is like 2 or 3 ohm meters, that's pretty conductive. And if you're sitting in a rock that's 2 or 300 ohm meters, that's moderately resistive. So yeah, and the EM can see that as well, but it's you got to watch it. They're not really apples to apples stories sometimes. Yeah.
I'll just add one thing, that the sort of convention change between the DIGHEM system over the years, this is impacted in the merge grids we published. Like occasionally the 2 adjacent surveys were not combined for sort of easy viewing because of the mention. Actually, I'll show you when my examples come out, because of exactly what Adam mentioned, is that because they weren't all post-2000 surveys, they aren't, the absolute values are different, so they don't merge well. So you just gotta kind of think about it. Maybe you get lucky with some overlap and you can operate it.
Exactly. So if you have this ground calibrated and this high altitude calibrated, you can use this as your absolute and re-level the old one to that. If you don't have that, it starts to become pretty subjective.
Just stay within the survey boundary of your interval, you see.
That's okay. On the gravity, it's been a long time since I did a lot of gravity modeling, so I get that the technology's changed a lot. So when you're talking about the different size of anomalies that you can see with the different methods that that are available, satellite versus the fixed thing versus when you are looking for your smallest features, what are you using to get rid of any regional trends? Is that kind of collected, or you trying to see question? You know what I mean? Like there's always going to be some sort of big regional trend that can start masking the smaller features. So I'm just wondering what.
On the radiometry side, that's usually mostly removed right away.
Okay.
Because if it's a fairly linear trend, the gradient doesn't see too much of that.
Okay.
So those smaller features are still going to come out. Typically, we are flying radiometry, so we're not too concerned about that. We actually usually are trying to look for bigger things because we can see smaller near-surface features that we're not terribly interested in. So we are usually looking at changing the wavelengths and doing different filtering to make different size features appear in the grid that you're looking at. On the gravimetry side, where you're measuring just gravity, you can do different processes to remove that linear trend of the regional, yeah. And I can talk to you about that.
One of, Adam, as we asked him to, and we'll have some examples of radiometrics. Radiometrics doesn't get loved much by geophysicists. We sort of say it's a geophysical measurement, but really, to me, it's a geochemical parameter. And so, but most geochemists regard it as the bastard child. They don't really want to touch it. And so it kind of, you don't really find a lot of people that embrace radiometrics as much as I think it should be, because what Adam said was true. It is coming from the upper, few inches, centimeters. But then, like in geochemistry, how did it get there? The stuff right at near surface is usually wind-blown or some exotic. But if you go over, as I think Adam will have an example from the Casino Porphyry deposit, there is a zone that's got 300 meters of regolith, and it has a strong potassium anomaly. It has been preserved in that, and that's coming from the upper 10 centimeters. So that that's attached to the original alteration system that's now covered by all this oxide zone and supergene. It's persisting. And I had a bit of a discussion with some colleagues about why isn't there more of this done, in the Yukon or in Alaska? And people say, oh, it's the snow. We have so much water. And you say, but isn't large parts of Alaska semi-arid? The amount of snow is actually not that much. And what you find is there's a lot of people love flying magnetic surveys. And the more mag they can get, the more points they get. But they don't fly radiometrics because they don't know quite what to do with it. It doesn't have the same kudos. And so we see a deficiency in both the Yukon and Alaska in the mapping information that I think radiometrics would actually really contribute with. And it's pretty simple techniques, the ratioing and stuff like that. It's there's things we could do to understand better how those signatures get into the upper soils. But in many places they're there, and accept the fact. And if it tells you something about the alteration, that adds a lot to discrimination when you combine it with EM and conductivity and density. So it's kind of like, what was it, 1% of the surveys are radiometrics? So clearly it's the poor man in the room.
And I'll kind of add to that, we all collectively see, from these examples, how useful it might be. It comes up every cycle, especially with the fixed wing mag surveys. There's always you can add radiometrics for certain costs. But in order to get that part out of done, I need support. Basically, if the public is clamoring for radiometrics, then I can push for a reduced survey footprint, say at the cost of getting radiometrics or reduced line spacing or whatever. It can happen, but without the sort of call or cry for it. And there are places you can say it is difficult to take the data, but Ken makes a good point that it's pretty dry in a lot of Alaska. And that snow, this time of year in northern Alaska, there's just a few centimeters and the water content is very low. I would argue against some people that you could get the data if you timed it correctly.
Are you going to show some examples
Yeah.
of what you have?
Yeah, some of them are in similar terrain to this, but next door, just where the data, but the Canadians haven't been much better, and they don't do a lot of radiometrics in these environments, in the upgrade they have. Like some of the data from Casino was 1994. It's stunning. And they did ground follow-up, and they showed discrimination between a felsic rock and this potassium-rich intrusive rock. And it didn't seem like any surveys were done on follow-up on that. So it doesn't have the advocacy. There's not a lot of dyed-in-the-wool radiometrics gurus out there. And as I say, the geochemists are sort of seem wary of it. They're not as comfortable with it as they are with conventional geochemical techniques, is my impression. And geophysicists will acquire the data, but it's an orphan once that data's been acquired. So it lacks a constituency, but I think, you know, people with practical problems that want to add layers, radiometrics should be part of that story. It could be, and it's an easy one, I think, to also figure out where it's not showing something. So the concept of false positives to me is less of an issue with radiometrics, because we know you've got water, game over, right? You're not going to have real bodies of water. And topography can have some effect, but there's even some of the work the GSC did showed that even in residual soils, the amplitudes may be reduced, but the ratios stay relative the same quite often, that the mobility of the radio elements actually is friendly to sort of keeping the ratios intact, so you can still do some discrimination on the basis of using ratios. So anyways, it's just Abraham and I talked about this last year, and sort of like I looked into it a bit afterwards and say, yeah, the mag constituency is a very strong one, and they want to get more coverage. And I understand that. It's not too, but sometimes there's balance depending on, you know, what sort of terrains you're looking at, what sort of applications.